Hi everyone, my name is Chen Hao from Concordia University in Canada. I'm presenting the technical track paper co-authored with Dr. Hen Li and my supervisors Dr. Peter Chen and Dr. Wei Yishang. So when a system is running, it usually generates logs showing the execution behaviors of the system. Developers and operators usually use logs to debug or monitor the system. They're often treated as the most important or even the only source of information for debugging and maintenance. And apart from that, logs can also be used in a variety of tasks, such as failure diagnosis, requirement tracking, program comprehension, and much more. Here is an example of some logs generated from HDFS. We will just take the huge message here as an example. We can see there's a log level, which is info level here, then the class name, some blue messages, and the purple dynamic variables. So basically logs consist of a verbose level, some static messages, and some dynamic variables. And logs are generated by logging statement, which is a snippet of code that generates logs. It also contains a log level, some static messages, and probably some dynamic variables. For the verbose level, they can be as low as trace or as high as arrow. Developers can configure the level for a system so that log levels lower than that will not be generated. We collect the recently resolved log-related issue reports from 9 open source systems, and we find that over 40% of the issues are specifically log level related. We can have a look at this issue as an example. The person reports an info level logging statement saying that the information log here is too specific and actually not needed by most of the users. In order to reduce the noise, a lower debug level is suggested. The suggestion was accepted and the issue was resolved. So if we set too high levels for some trivial system events, then there will be too many false alarms and a user will be confused. But in contrast, if we set too low levels for some critical events, such as a system crash, then very likely the critical information will be hidden in a tremendous amount of general information, or even cannot be generated at all. So in practice, deciding a proper level for a logging segment is an important yet very challenging task. And in this paper, we propose a deep learning-based approach to help decide log levels, and we achieved promising results. For the overall flow of our study, first, we start by extracting logging segments with their containing method from 9 open source systems. They cover various domains and were maintained, considered following good logging practices by many prior log-related studies. After extracting logging segments, we then randomly sample some ones to manually study their characteristics. Specifically, we study the characteristics of their logging locations and log messages by leveraging and refining the categories derived from 2 prior studies. For the category of logging locations, they are, for example, catch class and logic branch. And for the category of log messages, they are operation and variable descriptions, as well as negative execution behavior description. In our manual study, we classify the category of logging location and message for each sample, and we compute the distribution for each log level. We present the distribution of 2 categories of logging locations and log messages respectively for each log level. From the line chart, we can see there's a very different distribution of both the location and message for different log levels. So we can see that logging location and log message are important for the decision of log levels. We can also find that log levels that are further apart in order tend to have more different characteristics of logging location and log messages. And considering the ordinal nature of log levels, we can leverage this characteristic to help us decide the log levels. Driven by our manual study, we propose a deep learning-based approach to suggest log levels by leveraging the findings from our manual study. We first extract features from the source code. They are the syntactic context feature of logging code, representing the logging locations, and the log message feature, and the combined features of them. Then here we give a very simple example of how do our features look like. Here is a method declaration with a Boolean statement and an if statement inside. And within the if statement, there's a logging statement and a method invocation. So the syntactic context feature will go like this. We include the line numbers for presentationally. They do not really exist in the actual feature. Then we get the message feature with common preprocessing practices. Then the combined feature, we insert the message features into the syntactic one with a special mark indicating the start and the end. Then for the labeling of the training data, we use an ordinal approach to encode the vectors. Many other multi-class classification studies use one-hot encoding to encode the label vectors. In the cases that the classes are independent and do not have too much relation, it works. But for log levels, such as the relation between error and trace and the relation between debug and trace, they are definitely different. So instead of using one-hot encoding, we use a different ordinal way to encode the label vectors in order to leverage the ordinal nature of log levels. Then we form our approach as a multi-class classification problem, specifically a 5-class classification problem. So if we just randomly pick level as the result without any knowledge, the accuracy will be close to just 20%. For our deep learning framework, we first feed our features into a word embedding layer to learn the relationships among the tokens. We then employ a bi-LSTM layer to model the relationship between the log level and the vectors returned from the embedding layer. Finally, the output layer gives the result of each digit of the ordinal log level vectors. We can then get the final level result based on the vector. Then we evaluate our approach by proposing 3 research questions to evaluate our approach. And due to the time limitation, we only present a part of the results of RQ1 and RQ2 here. For RQ1, how effective is our approach in suggesting logging levels? We compare the results of our approach with the prior work, using ordinal regression model to suggest the log levels, which is the state-of-the-art in suggesting log levels. The right 2 bars show the accuracy and AUC score of our approach, using the syntactic context and combined features, respectively. And the blue bar shows the results of the baseline. From the bar chart, we can see that even we only use the syntactic context feature to suggest the log levels, our approach can still outperform the baseline. And our approach achieves the best results when both the syntactic context and the log message features are considered. In other words, the combined features has the best results. And then in RQ2, what is the performance on different log levels? The bar chart shows the accuracy of our 3 features divided by the actual log levels. From the chart, we can find that overall, syntactic and combined features have much better accuracy than the message feature in most of the levels. The log message feature may only provide helpful suggestions on some specific log levels, such as warn and error level. And the syntactic context feature show more consistent capability in making suggestions. So these are some selected findings from our RQs. For more detailed information, please have a look at our paper. In summary, we discussed what are the verbosity levels, and deciding log level is an important and challenging task. And in our manual study, we find that logging locations, logging messages, and the ordinal nature of log levels can be leveraged to help decide log levels. Leveraging those findings, we propose a deep learning framework that uses ordinally encoded vectors to suggest log levels. We propose 3 research questions to evaluate our approach, and we have promising results. So basically, that's the presentation. Thank you.
Hi again. Welcome everyone to the question and answer session of the paper DeepLV, suggesting log levels using Ordinal-based neural networks. Senhao Lee from Concordia University has joined for this question and answer session. I would like to thank him for the great video we have just watched. And please make your questions in the chat and he will be glad to answer.
Okay.
So we have already a first question from Jenderson Barros Candido. So hi, Senhao. Very cool to see your presentation. Do you have any thoughts on the differences between accuracy for different log levels?
Accuracy for different log levels.
Mm-hmm.
Yeah. So actually, in this part in RQ2, we just find that for different features, like for the syntactic context feature, it generally works well for most of the log levels, like from debug to arrow. And for the combined features, it also works well for most of the features. But for the log message feature, it only works well for a few specific log levels, such as warn and arrow level. And we take a quick look into the logs that belong to those levels, and we found that the probable reason for this might be that there are many specific words or phrases in those levels, in war and arrow levels. Like in war message, there might be a severe issue for some class, for some file, so that the neural network probably can find this and give a more accurate suggestion for warn and arrow level for the message feature. But for the other two features, they generally work well for most of the log levels. And that's what we found in this part.
Great, thank you. We have another question from Sukmin Kang. Are logging levels numerically balanced? If not, did you balance them during training?
Numerically balanced? I guess he means is the distribution of log level balanced among the data set? I guess so. Mm-hmm. So if my guess is right, I would say it's really not balanced. Like for trace level, there is only like 5% around that in the study system. But there is a majority of info and debug or warn levels in the systems. So the data is not really so balanced.
Okay.
For the different log levels.
The second question was, what is the per class accuracy effect of using the ordinal training that you mentioned?
Per class accuracy effect using. I guess this question is similar to the specific results for different log levels.
Yeah, so indeed, he added a comment.
Yeah.
I mean, it's the same number of warning statements as error statements, and so on.
It's the same number of warning statements as arrow. Yeah, so I think in our paper, we have a preliminary results for the distribution of the log levels. And yeah, the percentage of log levels in warn level and arrow level are similar. They are both around 24% in a data set. So yeah, warn and arrow level are similar. They have a similar distribution.
Mm-hmm. Mm-hmm. We have another question from Pinja Hen. So great talk. Is it possible for DeepLV to learn incorrect log level prediction strategies, given that there are some errors in the training dataset? And how do you plan to deal with those errors? For instance, learning with noise?
Yeah, I think it's really a challenging question for most of the deep learning related software engineering papers. Yeah, maybe there are some very few cases in the training set that are not really correctly written in the data set, but we cannot really check every logging statement to see if they are really correct. And it's also kind of a subject work to say if they are correct or not. So the effort that we can do is to increase the training set, to include more subject system to train the data, and also use the well-studied systems like Cassandra and the HBase that are really studied well in the prior log-related studies. And those systems are really well maintained and they have a very long history of the development. So that's we can do to deal with this challenge. And I agree that it's an interesting and challenging problem for the training data set.
Okay, we still have some time for questions. My question would be, you couldn't comment on all the research questions, as you said during the presentation. So can your approach benefit from transfer learning? That was your research question 3.
Approach benefit from, yeah, due to the very restricted time of the presentation, we didn't really say a lot of the findings for this RQ. So basically in this RQ, there are 2 parts. One is cross-project prediction, as many other deep learning papers do. And the other part is we enlarge the training set for each system by combining the training data from other systems. And then we do the prediction on the target system to see if the performance can benefit from enlarging the training set. So for the first part, cross-project prediction, yeah, of course, we can still achieve a very good result for it. And yeah, the accuracy is also reasonable. Of course, it cannot be better than the self-prediction, but I would say the result is also reasonable and good. And for the other part, the enlarging the training set, as we maybe you can see that we have 9 subject systems, and 8 are from Apache, and 1 is Elasticsearch, which is not a part of Apache project. So the interesting part is enlarging the training set really work well for the 8 Apache systems, and they can benefit from enlarging the training set from each other, but it doesn't really work for Elasticsearch. The performance decreased a lot by combining the training data from other 8 Apache systems. So for this paper, we didn't take a manual look into the real reason or potential reason for that, but I guess it might be an interesting direction for future work that can take a look for different types of the systems. Indeed. Like
we have time for,
systems.
We have half minute for a very last questions from Sina Goramian. So great talk, how everyone like it. Did you encounter any cases that the predicted level looks more accurate than the actual level?
The predicted level looks more accurate than the actual level. The predicted level looks more accurate than the actual level. I think probably it can be possible, but we didn't have a manual look into those cases. But I think it might be interesting to have a look.
We can discuss this in the discussion room starting now. See you in 3 seconds in the following talk. See you.